Professor Lin. Good afternoon, everyone. This is Yong Park from Korea University. Today, I will introduce our work titled "When IoT met Augmented Reality, Visualizing the Source of the Wireless Signal in AR View." Dr. Sang-Ki Yoon and Dr. Gyuhan Kim and me will work this together. And let me start the presentation. Internet of Things is smart infrastructure and device service technology that connect device and human. It has a variety of applications such as smart farming, smart factory, and home IoT. One of the important issues on IoT is how intuitively the user interacts with the IoT devices. Introducing augmented reality to IoT is one of the best ways to solve it. Here, I show the examples how IoT device can interact with the human with AR support. Let's consider the scenarios of smart factory and smart farming. Usually, the holding on AR device such as smart glasses and tablet. By including the area with IoT sensors and controllers within the camera angle, user can immediately recognize the data retrieved from the IoT device, such as pressure, humidity, and temperature. Also, by clicking the IoT device within the AR device screen, we can control the IoT devices such as changing the water supply level and update the monitoring interval. Although the IoT with AR is conceptually great so far, there has been no particular technique to enable it. The main challenge is that it is difficult to localize IoT device within the camera image and visualize data on top of it, which we define it as IoT visualization. The two requirements for the IoT visualization are: first, we need to recognize IoT devices and find the location of them in the camera image. Second, we should match the ID of wireless data is sent with the recognized IoT device. So we define such an IoT device identification plus matching with the data as IoT visualization, which is the main problem that we try to solve in this work. So how can we enable the IoT visualization? One straightforward way might be using computer vision. With the support of powerful deep learning technique, it might be possible to recognize IoT device and track the location of it. However, the main challenge is, given the multiple IoT devices with the same appearance, we cannot match the recognized devices with the data that they are sending. Unfortunately, such a situation is very common in industrial IoT and many IoT use cases. Another possible approach would be a wireless device tracking-based approach. Here, using the wireless data frame from the IoT devices, it defines the relative position of the IoT device from the AR device and convert it to the position of the IoT device in the camera angle. In this case, matching the received data from frame with the identified device is not a problem, but the challenge is such a solution requires a very accurate 3D position tracking. Also, getting the camera orientation is mandatory for visualization, but existing 3D position tracking techniques does not support the receiver orientation tracking. In this talk, we introduce BizIoT, which is a novel approach to enable IoT visualization. It tracks the wireless sender position only using the angle information. To estimate the angle with high accuracy, it uses the phase information of wireless signal combined with gyroscope sensing data. This technique has no reliance on computer vision technique, so it has very low computational complexity and it can track the location of the device in situation that computer vision does not work well, such as dark light condition. So let's first talk about how to find the location of the IoT device in the camera image. To understand it, We first need to understand the relationship between the position of the object in the real world and its position within the camera image, which is called camera geometry. Given the 3D object, so 3D location of the objects x, y, and z, the location of the object in the camera angle is represented as fx over y and fg over y, where f is the focal length of the lens. Here, the x, y, and z are the Euclidean distance in x, y, and z axis, which is called Cartesian coordinate. Another coordinate system that represents x, y, z using the angular relationship is called sphere coordinate. It represents the position of the object using 3 parameters r, theta, and phi, where r is the one-dimensional distance between the origin and the object, theta is the elevation angle in z-plane, and the phi is the azimuth angle in xy plane. The relationship between the Cartesian coordinate and the sphere coordinate is as follows in this function. Our important observation is that when you represent the position of the object using the sphere coordinate rather than the Cartesian coordinate, we can find the position only using the azimuth and elevation, where the distance r is cancelled. This is great advantage for the wireless tracking because while the distance estimation relying on the RSSI is unreliable and easily corrupted by noise, the angle estimation based on the phase difference of the multiple antenna is much accurate and reliable. To see how accurately we can find the object location only relying on the azimuth and elevation, we conducted a simple experiment. Using Microsoft Surface tablet, we took the pictures of the objects. Then, using the ground truth azimuth and elevation angles, we estimate the position of the object in the picture and compared it with the ground truth position. The result shows the median and maximum errors are only around 5 and 20 pixels, which is likely to be measurement noise. This result shows that the angle-based position tracking is very accurate. Then the next question would be how we can estimate the azimuth and elevation angles between the IoT device and the AR device. If the receiver device has multiple antennas and if you can observe the phase of the signal from multiple antennas, it is possible to estimate the angle of arrivals using the phase difference. Such a technique is very widely used in many existing device tracking solutions. However, the problem is it is usually only one-dimensional angle of arrival between the transmitter and the receiver, while the need for visualization is two-dimensional direction of arrival. The relationship between the phase difference and the two-dimensional direction of arrival is modeled by following equations. Here, the main challenge is how to separate the azimuth and elevation from the measured phase difference. It is very difficult to solve when the receiver has only 2 antennas. So many practical radar systems use complicated antenna arrays such as uniform circular array, L-shaped array, and parallel linear array. However, such kind of antenna system are not applicable to AR devices. So we propose a new azimuth and elevation estimation technique for the AR device with 2 antennas. The main idea is exploiting the rotational movement of the device. During the initial phase of IoT visualization, the user rotates the device along the Z and Y axis. The amount of rotation is accurately estimated using gyroscope. During the rotation, we also collect the phase change over time. Finally, by combining the phase change and the rotational angle change over time, with IoT can accurately estimate the azimuth and elevation angles. I first introduced how this IoT estimates the azimuth. Suppose the user rotates the device along the z-axis. During the rotation, the azimuth changes while the elevation remains the same. When the transmitter is aligned to the y-axis, the azimuth angle becomes 90 degrees and the phase difference becomes 0. Given that, we detect the current azimuth angle is 90 degrees. Then you start to track the azimuth change using the gyroscope. Finally, at the time that the user stops rotating the device, you can find the current azimuth angle of the device by adding 90 degrees to the rotation change estimated from the gyroscope. Likewise, we can also estimate the elevation using the rotation of the device along the y-axis. After azimuth estimation phase is completed, the user rotates the device along the y-axis as well, which changes the elevation angles. And the IoT device aligns to the horizontal plane of the AR device. The elevation angle becomes 90 degrees. At this time, the phase difference is maximum. Then it starts to track the device rotation along the y-axis, which is lower. From the estimated lower, we can finally estimate the current elevation using this equation. Given the introduced azimuth and elevation estimation technique, we can localize the position of the IoT device in the camera image. However, in order to use the IoT visualization in practice, we have to address a few additional challenges. First, we need to resolve the issue of the ambiguity of the angle problem. Where given the phase difference measurement, there are multiple possibilities of real angle arrival. Another problem is how to maintain the tracked position when the user moves and rotates the device after the tracking the device. The filtering the non-line of sight device is one of the issues. In this talk, I'm not going to introduce the detail how we address these problems, but you can find detail in the paper. Now, I'm going to show the performance evaluation result of BizIoT. For the prototype development, we used Microsoft Surface 2000 AR device, which has built-in camera and IMU sensor. We connected the USRP software radio to the surface, which encodes and decodes GP frames and estimates the phase difference in real time. Also, we implemented the location tracking and visualization algorithm and learn it in real time. In our prototype design, we track GP device because it is more widely used for IoT systems. However, this technique is directly applicable for Wi-Fi device visualization without any modification. For the performance comparison, we implemented UV cars similar to BizIoT. It estimates the azimuth and elevation angle using the rotation of the device triggered by user. However, its main application is indoor application, so it cannot be directly applied to the wireless source position visualization. So we implemented UV cars only for estimating azimuth and elevation and visualize the source using our technique. Here I show the tracking performance evaluation results. When it visualizes the position of the GP device with the distance between 1 to 50 meters, BizIoT achieves the median position error of 134 pixels. On the other hand, UV is much larger positioning error. Also, BizIoT performs stable performance with the increased distance. The main reason that the BizIoT achieved higher accuracy than UV is because it exploits the gyroscope rotation information more aggressively in both Z and Y axes. Here, I show a few sample tracking results. These three devices are visualized with the position errors of 90 and 139 and 156 pixels. Here, The position error of node 3 corresponds to the median tracking error of the BIS IoT. So we conducted extensive visual study on visual perception with respect to various position errors. When the position error is 113, people considered it to fair to good quality. Here, I show the performance evaluation in various situations. The graph here shows the impacts of the interval of the tracking accuracy. When you use the frame interval of 20 milliseconds, you achieve the median error of 134 pixels. When the interval is 100 milliseconds, the median error is as much as 170 pixels. When I performed the experiment in outdoor environment, the median position error slightly reduced, but because it is less affected by the multipath fading in outdoor environment. Now, I'm going to finish the talk with conclusion and future work. BIS IoT is a novel technology that enables the visualization of the location of the wireless sender in AR viewpoint. In this project, we introduced the double sender position estimation technique based on the combination of camera geometry with azimuth and elevation. Also, we propose accurate two-dimensional direction of arrival estimation by combining wireless and gyroscope sensing data. We developed the prototype and enabled the real-time tracking of a GP device. For the future research goal, what we consider important is enabling the visualization without requesting the user to rotate the device. We believe by combining the wireless sensing with the computer vision-based motion sensing, we can achieve goal. Thanks for listening to my presentation.